So let's start off by drawing a right triangle. This angle is 90 degrees, and we're going to call this angle theta. Now, first of all, this side right here is the hypotenuse of the triangle because it's opposite the 90-degree angle. So this is the hypotenuse. This side is opposite our angle theta right here, so we're going to call it the opposite. And the remaining side, the third side, we're going to call the adjacent because it's right next to our angle theta. Now this is going to help us define the three basic functions in trigonometry: sine, cosine, and tangent. And these three functions are just ratios of sides in the triangle. So for example, let's start off with sine. Sine of theta, or sine theta, is equal to the opposite over the hypotenuse, where the opposite is the side opposite theta, and the hypotenuse is the hypotenuse, as we labeled in this triangle. Cosine theta will be equal to the adjacent over the hypotenuse. So the length of this side divided by the length of this side. And tangent of theta will be equal to the opposite over the adjacent. And to remember this, we have a mnemonic. So, ka, toa. And we think of them as three separate things. Let's box these off. So let's look at the first box. So the S in so stands for sine. The O stands for opposite. And the H stands for hypotenuse. The C in ka stands for cosine. The A stands for adjacent. And the H stands for hypotenuse. The T in toa stands for tangent. The O stands for opposite. And the A stands for adjacent. So that's a cool way to help us remember that sine theta is equal to the opposite over the hypotenuse, cosine theta is equal to the adjacent over the hypotenuse, and tangent of theta is equal to the opposite over the adjacent. Now let's go down and draw another right triangle. This is the right angle here, and this angle we'll call angle theta. So this angle is theta degrees. And this time we're going to label the vertices as well. A, B, C. Now let's find the sine, cosine, and tangent of theta. So to do this, we're going to use our mnemonic. So, ka, toa, to help us out. So if we look at so, the S stands for sine, so sine theta will be equal to, the O stands for opposite, so opposite over the H, which is hypotenuse. And in this case, the side that is opposite our angle theta is BC. And the hypotenuse is AC because it's opposite the 90-degree angle. So sine theta is equal to the opposite BC over the hypotenuse AC. Now let's look at cosine. Cosine theta, we know, if we look at ka, The C stands for cosine. The A stands for adjacent, so cosine theta is equal to adjacent over the hypotenuse, because the last letter in chi is h. So hypotenuse. And the adjacent in our problem is AB, because this is the opposite, and this is the hypotenuse. So this must be the adjacent right here. AB must be the adjacent. So we have AB over the hypotenuse, which we know is AC. So cosine theta is equal to AB over AC. And tangent of theta, we know, is opposite because of the O. The O is the second letter. So it's equal to the opposite over the third letter, which is A, so the adjacent. So opposite over adjacent. And we know the opposite is BC. We see it right here. And the adjacent is AB. So tangent of theta is equal to BC over AB. Now let's do one more example. This time when we draw a triangle, we're also going to have side lengths. We're going to call this angle theta. Label the vertices A, B, C. This is going to have side length 3, 4, and 5. Now let's find sine, cosine, and tangent of theta. If we use our mnemonic SOHCAHTOA, it tells us the sine theta is equal to the opposite over the hypotenuse. Opposite over the hypotenuse. And in this case, the opposite of theta is AB, and the hypotenuse is AC. So we have AB over AC, which is 4 over 5, because AB is 4 and AC is 5. So sine theta is equal to 4 over 5. Now cosine theta is equal to the adjacent over the hypotenuse. Adjacent over hypotenuse. In this case, the adjacent is BC and the hypotenuse is AC. So we have BC over AC, which is equal to 3 over 5, because the hypotenuse has length 5 and BC has length 3. And finally, tangent of theta is equal to, we see the T over here, opposite over adjacent. Opposite over adjacent. Now the opposite is AB, and the adjacent is BC. We know the opposite is equal to 4 and the adjacent is equal to 3. So tangent of theta is equal to 4 over 3. Now if we go down, we're going to draw the same triangle again, except with different side lengths. This is going to be theta still. I'm going to label A, B, and C. Or rather, let's change this. D, E, F. And this side is gonna have length 6, 8, and 10. Now let's find sine, cosine, and tangent of angle theta. So if we use SOHCAHTOA, we see that sine is equal to the opposite over adjacent. Sine theta is equal to the opposite over the hypotenuse. And in this case, the opposite is DE, and the hypotenuse is always opposite the right angle, which in this case, the hypotenuse is DF. So we have DE over DF. Now DE has length 8 and DF has length 10. So this is 8 over 10, which is 4 over 5. So sine theta is equal to 4 over 5. Cosine theta is equal to, if we need, we can use our mnemonic, adjacent over hypotenuse. Adjacent over hypotenuse. In this case, the adjacent is EF, and the hypotenuse is DF. So we have EF over DF, which is equal to 6 over 10, because we know the hypotenuse is 10, and EF is 6. And 6 over 10 can be simplified to 3 over 5. So cosine theta is equal to 3 over 5. Now tangent of theta is equal to the opposite over the adjacent. And we can check with our mnemonic. Indeed, tangent is equal to the opposite over the adjacent. We know the opposite is DE, and the adjacent is EF, so DE over EF, and DE is 8, and EF is 6. So we have 8 over 6, which is just 4 over 3. So tangent of theta is 4 over 3. Now you might notice that sine theta, cosine theta, and tangent of theta are all equal to the same things as they were in this previous problem. Sine theta is 4 over 5, right here, just as it is right here. Cosine theta is 3 over 5. Cosine theta over here is also 3 over 5. And tangent theta is 4 over 3, whereas tangent theta is 4 over 3 here as well. Now why is that? Let's look into that. Let's draw both of our triangles down here right next to each other. We have A, B, C. This is 90 degrees. This is theta. And this is 3, 4, and 5. And then we have our other triangle. D, E, F, right angle here, angle theta here, 6, 8, 10. Now first of all, we see that EF is equal to 2BC. We also notice that ED is equal to 2AB, or rather DE, we could write, is equal to 2A, let's fix that, AB. And that DF is equal to 2AC. DF is equal to 2AC. So, each side of this triangle is double the side length of this triangle, which means that these two triangles are similar. DEF is just a scaled version of ABC. And we know that if two triangles are similar, the ratio of two of their sides will be the same. So for example, the ratio AB over BC should be the same as DE over EF if both triangles are similar. Because these triangles are similar and these sides correspond with each other. And remember what I said in the beginning, that sine, cosine, and tangent are just ratios of sides. So if they are ratios of sides, then they should be equal if we take the sine of two angles in two similar triangles. So that is why sine theta for this triangle is the same as sine theta for this triangle. And this also tells us one other thing. It tells us that let's draw another triangle. And this angle is 30 degrees right here, and this is 90 degrees. This tells us that sine 30 degrees, cosine 30 degrees, and tangent of 30 degrees will always be congruent. Because we'll label this side x, this side 2x, and this side x root 3. If we make another triangle, another right triangle, that is similar to this triangle, 30-degree angle, except it is 2 times bigger, we see that both these triangles will be similar. So therefore, we just learned that sine 30 degrees, cosine of 30 degrees, and tangent of 30 degrees will all be the same in this triangle as they are in this triangle, because both triangles are similar, and we're finding the sine, cosine, and tangent of the same degree measure. It's the same 30 degrees.